Hi there, and welcome to my graphics video. Don't mind the green screen. It's just a cool little thing, trying something new for this video. First time, inaugural green screen bit. It looks really cool. Like, if this works, if now it's chroma keyed out, it's working as intended. I can be like anywhere in time and space. It's amazing. I really do love this, and it's only gonna be used for this video. It's great. Anyway, the scene I've chosen to render in this project is the Temple of Time from Ocarina of Time. Before I proceed, I'd like to credit two aspects of this scene. First is the Master Sword that you can find located on any old Sketchfab website. And second of all, the textures used within this level. Now, these are taken from a visual mod for Ocarina of Time. So, if you, and for context, this is being filmed at an undisclosed location. So, if you did, you know, want to use a mod on, let's say, you didn't hear this from me, but if you wanted to use it for a ROM of Ocarina of Time, you can. But again, you didn't hear that from me. I don't need Miss Nintendo coming along and attacking me and destroying my entire family. It'd be quite annoying, actually.
So you've seen my scene in Blender using the basic Eevee engine. It's time to see what it actually looks like when we run it through PBRT. PBRT is, I guess, best described as an extension of ray tracing, capable of producing some truly amazing scenes, being able to simulate how light works within the physical environment, hence its name, physically based rendering. Now, here's what I came up with. Now, a few things to note. This light in the scene is pretty blown out, like getting flashbanged in 7 Rebirth at every turn levels of flashbang. Now, you can also see an unsightly shadow, which stems from this in my Blender scene. What this was my attempt of creating the iconic window light from my reference screenshot in my image. Unfortunately, it didn't pan out. Additionally, I like to point out a weird quirk I might have encountered in PBRT. You see, these little circles are supposed to display the 7 sages symbols as they do in base Blender, but unfortunately they seem to have not come across onto PBRT despite everything being hooked up correctly as according to the image textures. But hey, even PBRT 3 didn't really work with Maya, so I suppose 4 has its quirks too. Now, let's move on to the rasterizer. Software rasterization works via taking vertices in of a model or some object and subsequently transforming the vertexes into a 3D space to properly place them within the scene before being able to output them as a 2D TJ image in this case. In my version, you'll see me reading the basic makeup of my OBJ models with the addition of the VT values, which are essentially one of my 2 additional features I've chosen to add into the scene, the first being texture support. The VTs of the model are taken in to create a vec2 set of texture coordinates. From that, we can then proceed to pass these texture coordinates down into a check function, which then, after taking the sum of the coordinates and ensuring the pixel is valid pixel, we can then return the part of the texture we need as a TJ color element and set alongside the X and Y position on the screen. Now, in the final product, you can see that the textures look a little off. That's the combination of a few factors. First off, the scaling of the texture is off because in order to get certain models to render, I had to scale down the UVs in Blender, and second of all, the UVs seem to not cooperate with the models of larger size. Note that this smaller model, the texture is perfectly fine, so I feel as though somewhere between the Blender to OBJ process, something about the UVs change. This UV issue is why a few of my models aren't even in the scene. For example, when I try to add in this particular platform into the scene, from everything I can tell the model's correct, but when imported we get this result. Not exactly optimal, so they didn't make the cut. The second feature I chose to add, in addition to the basic, is the Z buffer. Essentially, past a certain point, certain triangles will simply not be drawn if depth values exceed the stored depth value in the depth buffer, the pixel isn't drawn. Additionally, the barycentric coordinates used within my render operations allow the depth of a pixel to be determined with greater accuracy. The depth buffer is initially set to a stupidly high number to facilitate this process, which typically you'd set it to a far clipping plane like 1000, and it works perfectly well if you do, but I set mine to infinity, which works great as well. Before I move on to the ray tracer, let's talk about one very important feature in the rasterizer, which is the camera. The camera works by taking a perspective matrix that I created by using this equation online and adapting it for my code, obviously. This is used for a perspective division to get the coordinates of the model and where it is in the image. Now, there are 2 ways to change the perspective in my scene. First off is straight up changing the model matrix that holds the location of the object in model space, but this isn't exactly a camera, is it? So that's where these functions come in. The target function here essentially tells me where the camera is looking. For this, I set it to 0, 0, 0, just for simplicity, and focused on moving the objects, hoping I could position them correctly. By altering the I function, I'm able to change the position of the camera And while in the final scene I have a similar downward facing angle, unfortunately despite much trial and error in changing the values, I couldn't get the exact shot I was looking for. I would also like to note that I took the Vec3 definition given to us initially and used it to create a Vec4 definition to facilitate storing values from matrix multiplications which hold 4 values, so that I could even perform a perspective division successfully in the first place. So to conclude, while I have all the features to facilitate a software rasterizer, there are a few kinks to be worked out. One of which is importing of the models and their UVs, as this seems to be the downfall of my scene here visually. As far as I can see, the models in Blender are fine, even after multiple renditions, so if I were to do this project again, I would actually take a look at my code that loads the model vertices, and specifically the UVs VTs, to make sure it scales to large models with more complex shapes. Additionally, I would revise how the perspective camera works with models in the scene, as while it works, I would instead give each model their own model matrix they can inherit from to further fine-tune their positions as well. In the RayTracer, you'll see all my models fall perfectly into place. Rasterizer was unfortunately not so lucky. Now, where my rasterizer may have left a little to be desired in the looks department, straight away you can see an improvement in the RayTracer. Now, this is because I was building this off of a lot of pre-made code compared to the rasterizer, such as the bounding volume hierarchy, which simply creates bounding boxes around objects in the scene and places them in a tree. The lowest nodes of the tree typically hold bounding boxes of individual objects, while the higher you ascend, you'll see that these nodes become groups of objects, meaning that when we cast a ray into the scene, you're able to discard large pieces of the scene from any calculations involving intersections because it never hits it. Moving further into the code is a JSON config file. You'll find the basic camera movements here, allowing you to set the position of the camera where I want it to. So unlike my attempt at rasterizer, you can see clearly here that I'm able to replicate the perspective of the original scene. Now, RayTracers work by firing rays from the camera into the scene, and upon intersections with certain materials, we can determine how light will interact with the scene. In this image, you can see a mirror shader that came with the starter code. The light is reflecting perfectly off the material. Now, I wanted to add a metallic material to the scene, so I took this perfect mirror shader and made a few changes. To start with, I let myself be able to change the base color and reflectivity values before moving on to adding roughness into the reflection ray, as it's about to reflect. I attempted to achieve this by generating a random number for the XYZ values, circular radius of the place the ray intersects, with the object thus allowing the light to randomly disperse in the scene, like a metal would. Now, the end result is this. Now, it becomes a little difficult to determine how effective the metal shader is without the presence of anti-aliasing. Anti-aliasing would allow a much sharper image, and we're able to see if this is working in this project. Now, while I'm unable to implement it, if I were to revisit this project, I could effectively test for changing the values of the roughness and reflectivity to just see how effective it is. The ray tracing in One Weekend trilogy books were pretty important to understand the theory behind this material, as well as a Microsoft Paint example by Bryce that I've replicated for this section of the video. So, while not many extensions have been made to the base code compared to my rasterizer was put together solely by me from bits and pieces I found around, I have been able to successfully implement my initial scene into the ray tracer as opposed to the rasterizer, with ray casting's intersections working well with my scene. The textures working via the texture Lambert shader also work seamlessly with the project, although some models' UVs have been returned to their default shape. Like in the case with the rasterizer, we had to change the makeup of these models to work. Finally, you can see one of the walls rendered in the background of the image. I chose not to add the others in the image as it would add unnecessary time for each render attempt, and in the original scene, while yes, I modeled walls in the Blender file, realistically they aren't present in the final version, so I decided to remove them. Overall, while my ray tracer was produced a much cleaner result than the rasterizer, I feel that it's more so because a lot of the basic infrastructure was built in for me, and while when coupled with resources like ray tracing One Weekend, some neat features can be implemented, on the other aspects like the config file that proved useful, I feel I could have done more if I had taken the time to really sit down and dissect the code in order to add more features easily. As while RayTracer theory remains the same across resources, my code base and the book's code base, the surface level, pretty different, making it a little bit difficult to translate features over, hence my shaky attempt at a metal shader. So right now here are my 4 images on screen, the initial reference, PBRT output, Rasterizer and RayTracer. Now, if you were to ask me, I feel like the RayTracer is the best looking overall out of all of these, since, well, it is kind of all there in the scene for starters, and overall looks the cleanest even without the addition of anti-aliasing. However, while rasterization didn't come out the way I was hoping, I have learnt a few things I want to take into consideration should I do this project again. First off, I really wish I could have gotten the camera in earlier, because while yes, the camera functions, and as a perspective camera, it isn't perfect, and is rather fiddly in how it actually sees the scene around it, Additionally, I want to look into how to properly translate UVs into the rasterizer, as my Blender versions not only messed up the objects even rendering in the scene in the first place, but you can see that even with the code I implemented, certain models simply do not have the textures applied as expected. This is especially odd given the example of 3 squares I gave earlier. On the ray tracing side of things, I would like to go back and add in a variety of shaders in addition to the metal shader, as well as look into how I might replicate the lighting effect that I made in the initial Blender scene to bring it in line with the original reference image. So yeah, that's about everything I wanted to cover from this video. So I hope you've enjoyed it. And with that, goodbye.